Second.
And don't forget there's a negative there.
Yeah.
In other words, this happens in the pulse reference frame, 20 meters and negative 57.7 nanoseconds. From the pulse point of view, the right door is going to close before the left door does. And then the third event, better happen after the second event in this time frame, because the pole is crashing into that door. It's got to crash into that door in both frames. It can't suddenly, mysteriously, it never touched it. Event 3, x prime is equal to 2 times 10 minus 0.866c times time, which was 7.698 times 10 to the negative 9.
It's 16 meters.
It's 16 meters.
Yeah.
And that makes sense, because when the right side of the pole touches this barn, touches the right side, again, for the pole's reference, the pole hasn't moved at all. And so the right side is at 16 meters. If 0 meters is here, this better be 16 meters in the pole's reference frame. And T prime becomes 2 times 7.698 times 10 to the negative 9th minus 0.866 over 3 times 10 to the 9th times 10. I canceled out one of the C's already.
Negative 4.2 times 10 to the negative 8 seconds.
So this happens at 16 meters. Negative 42 nanoseconds. So from the barn's point of view, pole makes it in, both doors close at the exact same time, and then the pole crashes into the right side. From the pole's point of view, the first thing that happens is the right door closes, or from your point of view, the right door closes, then the pole smashes into it, then the left door closes. Because the left door doesn't close till the pole's completely inside it, and if the barn's only 5 meters long from the pole's point of view, this, it has to be sticking out the other side before the left side gets to here. And so we now have a mechanism for looking at the relationship between what's happening in two different reference frames.
I have a question. Is that 3 times 10 to the 9?
Yes.
Oh,
Oh, that should be 8.
yeah.
I assume you typed it incorrectly.
Mm-hmm.
Okay. I thought something was off when I was looking at this, because I was doing it in my head and I thought, wait a second, it's supposed to be a negative number. But, okay, that explains it. Now, I'm curious, Austin, did you see the 9 and go, he meant 8, or did you just completely ignore what I wrote there?
It looked like an 8
Okay.
for my reference frame.
That's the nice thing about Genius, is you can look at something and see the reality.
Mm-hmm.
Getting closer. 3 more derivations before we get to equals MC squared. The next 2 derivations are a lot shorter. All right, any questions before I erase this and we look at velocity addition? All right, I'm gonna change that V there because why on earth would I want my this to be consistent? While I'm thinking about it, what you're doing on Thursday, the lab, I'll bring it in. Nothing for you to print out. I will bring it to you. I'm just gonna adjust this. You. All right. So what we have here is we have our 2 reference frames here, but within we also have some object that is moving. And so how fast it's moving, I believe W is what I picked. Yeah. This is the velocity of the object, of the particle, with respect to the S prime frame. So you're in the rocket ship and you you're in the back of the rocket ship and you get your slingshot and you sling something towards the front of the rocket. This is how fast it's going relative to you. Meanwhile, back on Earth, they view this thing going at a different speed. Because we've already talked about things going slower than the speed of light will not get to the speed of light. You can't pass it. So if you are in a car, make it a station wagon-ish. So you're driving along in a car, someone in the back of the car throws an object to the front. So the velocity of the car with respect to the ground, which is generally how we measure speed of cars, is, let's just say, 50 miles per hour. The velocity of the ball, we'll make it a ball being thrown, with respect to the car, is 10 miles per hour. So you're on the way back, you throw something at 10 miles per hour from your point of view towards the front. How fast is the ball going with respect to the ground?
60.
Formalizing that, the velocity of the ball with respect to the ground would be the velocity of the ball with respect to the car, plus the velocity of the car with respect to the ground. As long as those letters are the same, as long as this is with respect to that, and this, and the same thing is with respect to the other object, we're good. So there's the first letter, there's the second letter, the middle two need to be the same, and it's legitimate math. This is Galilean relativity. So as Jesse said, velocity of the ball with respect to the ground. What the heck? Let's be slightly more formal. 60 miles per hour. So if you're in a rocket, if we treated this from a relativistic point of view, the velocity of the rocket with respect to the Earth is 0.8 times the speed of light. You throw a ball forward, and the velocity of the ball with respect to the rocket is 0.6 times the speed of light. If Galilean relativity were true, then the velocity of the ball with respect to Earth, this is if Galilean relativity is true. I guess I also use GR for general relativity, Galilean. Then this would be the velocity of the ball with respect to the rocket, plus the velocity of the rocket with respect to Earth, would be 0.6 c plus 0.8 c, which is 1.4 c, which violates what we say about relativity. So we need to somehow reconcile that. And the velocity of the particle with respect to s is v, and the velocity of s prime with respect to s is u. Just finish those definitions out. So w is how fast the object's going with respect to the prime frame. So it's just the distance in the prime frame divided by the time in the prime frame. If we establish sort of a coordinate system properly, then we can just simplify that to x prime over t prime. The initial x prime, the x prime initial and t prime initial will both make 0. So this is gamma x minus vt, or, sorry, x minus ut, over gamma t minus u over c squared t, c squared x. Trying to put this in terms of what does the s prime, and in English, trying to get it in terms of what S frame sees. Gammas cancel out. I'm going to divide top and bottom by time. So times 1 over time over 1 over time. So I get x over t minus u divided by 1 minus u over c squared x over time. Well, that's just the distance traveled in the s frame divided by the time in the s frame. In other words, this is how fast the particle is going in the s frame, which is just v. So this becomes v minus u over 1 minus u v over c squared. Where's w? Compare that to the Galilean relativity. The particle with respect to the prime frame is W. That's W right there. The velocity of the particle with respect to the S frame was V. And the velocity of the rocket with respect to Earth, or the S prime in reference to the S, is U. So Galilean relativity says that V equals W plus U, or W is equal to V minus U, which is our numerator right there. That's always going to be the case. Whenever I'm trying to solve the relativistic velocities addition, I do it in Galilean relativity terms first, and that tells me what the numerator is. The denominator is just going to be those two velocities right there, or those two speeds right there, and the sign will be the same. So, if I wanted to solve this problem, I have V is equal to W plus U divided by 1 plus UW over C squared. Again, signs are the same, and the two I'm working with are the same two I work with in Galilean relativity, and because it's plus here, it's plus here. And so this gives us 0.6C plus 0.8C divided by 1 plus 0.6C, 0.8C over C squared. And this better give us something less than the speed of light. Or perhaps it's another Nobel Prize for us.
Well, we already have so many.
How do I have so many?
I said, no, but we already have so many.
Oh, yeah, you know. Perhaps we should get something under C just to let other people have a chance to get their Nobel Prizes.
Yeah.
Something.
Zero 0.9459.
That's too late. This is how you add velocities, relativity style. You got to ask a question? All right. Free to go. Rewrite that. Could just take a whole stack with you. All right, so we got the S frame right there. I know it's shocking, but we're going to do that. And you know what? Let's just keep you on your toes. S prime. It's traveling at some speed u. But this time, we're going to make the particle travel in a different direction. I'm not saying it's going to go backwards, it's going to go off at an angle. So the particle is now traveling like that. The velocity of the particle. We'll look at it from 2 points of view though. So obviously, what we just did was dealing with velocity in the same direction that the prime frame is going in. But what if it's not going in that direction? Suppose it's going perpendicular to it. In other words, we do have components here. We're going to call that V sub x and V sub y. Now V sub x we already know, that's what we just derived. V sub y on the other hand, that's what we need to figure out. So V from y in the S frame is just dx dt. Oops, try that one again. dy dt. Assuming, I guess I should label it. X, y, x prime, y prime. Vy prime is equal to dy prime over dt prime. I know that y prime and y are the same thing. The relative effects happen parallel or anti-parallel to the movement of the speeding object. So this is the same as dy over d times gamma t minus u over c squared x. Now we're not having this thing accelerate. Gamma is a constant, so I'm going to pull it out. U is a constant for a problem. So gamma comes out. And then I'm left with dt minus u over c squared dx. Multiply top and bottom by 1 over dt. And we get dy dt on top. And we get gamma over 1 minus, or over gamma times 1 minus u over c squared dx dt.